Hi, I'm Matt Simpson from SAS. In this video, I'm going to talk about how to incorporate auxiliary information into your model using Bayesian methods. In particular, how to automatically create reasonable prior distributions using SAS Econometrics software. Bayesian methods allow you to take into account information in addition to the data through the prior, but it's not easy to do. Computationally and mathematically, it's not a problem, but conceptually, it is quite difficult to translate outside sources of information or vague intuitions into mathematically precise prior distributions. The solution is to think real hard about your priors. I have a SAS Global Forum paper and presentation that discuss in detail how to do this. This demo focuses on how to make the process easier in SAS using some nifty tools. Code for the examples in this demo and a URL for the associated Global Forum paper are available on GitHub. I will give you the URL for the repository at the end of the demo. The beginning of the prior selection process is a reasonable default prior. The main characteristic of this prior is that it is weakly informative for the questions you care about. No prior can be uninformative or weakly informative for every possible question, so you need to focus on the questions you are trying to answer with the analysis. In practice, a weakly informative prior is spread out, but not too much. A good way to operationalize this criterion is to use a normal distribution with mean M and standard deviation S. The value of M should be chosen to be the value you think is most likely, or perhaps the null hypothesis for that parameter, depending on your inferential goals. The value of S should be chosen so that M plus or minus S is the most extreme value you think is realistically possible. This implies that values more extreme than you think are possible happen 32% of the time in the prior. So the prior allows crazy things to happen, but it discourages them. Choosing good values for M and S depends on the type of parameter in question. For a detailed explanation of these default priors in linear regression, see the paper and associated presentation. I will only briefly discuss them here. The prior on sigma is a truncated normal since sigma cannot be negative. A common choice here is an inverse gamma prior on sigma squared. That prior is often problematic, though, because it will not let sigma be too close to zero no matter what the data say. This can even cause computational problems. The truncated normal prior on sigma avoids both of these issues. Since different covariates have different units, interpreting them relative to each other in order to construct priors on regression coefficients is quite difficult. By transforming the covariates or taking into account the scale and units of the covariates and of the response in the prior, you can make interpretation much easier. Typically, this means either log transforming the response and relevant covariates, or centering and scaling them by their sample means and sample standard deviations. For some of these priors, we need the sample standard deviations or sample variances in order to define the prior. In log-log models, you can interpret the coefficient as a unitless elasticity. For other continuous covariates, the general idea is to interpret the coefficient in terms of how many standard deviations the response changes after a one standard deviation change in the covariate. Here I center all the betas on 0 since the typical null hypothesis is no effect. But you could do something different if that is more appropriate for your problem. Next, we have to pick values for each of the different types of S's in the prior variances. A good default value in any of the regression coefficient priors is S equals 4. For the intercept, we need to allow for a much wider range of variation since the value of the intercept is strongly affected by the values of all the other regression coefficients. Setting S sigma equal to 1 implies that the crazy value of sigma that we never expect to see is the sample standard deviation of the response. This makes sense because in OLS, the error standard deviation is bounded by the sampled standard deviation of the response. Again, this prior allows for values larger than that about 32% of the time. For more information about why I chose these particular values, there's a URL from my SAS Global Forum paper discussing this on the bottom of the slide. To implement these priors in PROC QLIM, you first have to manually transform the data. Then you compute sample summary statistics so that you have the sample variance of responses and covariates available when you construct the priors. Then you need to plug all this information into the formulas to get the default priors, and you need to turn them into prior statements for PROC QLIM. The prior statements are in the blue box on the slide. This process can be quite tedious. Instead, I have a semi-automatic process you can use to automatically generate the prior statements for you. Scripts for this process are available on GitHub at the URL shown on the slide. The process is 2 steps. In the first step, you pass a data set to a SAS script called autopriorlinear.sas. That script transforms the data set and produces class and model statements to fit a regression in PROC QLIM. It also creates a prior distribution data set. In the second step, you pass the prior distribution data set to the SAS script prior statements.sas. This produces the prior statements for PROC QLIM or PROC CountReg. You can also manually create the prior distribution data set if you like. Let's look at an example. This is contained in the SAS scripts autopriorrun.sas in the GitHub repository. In the first step, you need to tell the script which variables you want to include in the model and how to transform them. This is just a data set with several columns: variable name, variable type, transformation type, and an indicator of which variable is the response. Next, you define two macro variables that point to the original data set and the variable data set you just created. Finally, you create macro variables that define the value of S for each parameter type. Here you can also define the prior means for several parameters, but I've set them all to 0 by default. Then you run the autopriorlinear.sas script. This generates the transform data set, which you can see on the slide. It also generates the prior data set shown here in the middle of the slide. The model statement and class statement are also created as macro variables that you can use when you call PROC QLIM later. Next, to generate the prior statements, you only need a macro variable named prior, naming a data set that contains the prior information. The last step created that data set and macro variable for us. So we can just run prior statement.sas to generate the prior statement. The prior statements are created and stored in the macro variable prior statements. So now calling PROC QLIM using the generated model, class, and prior statements is straightforward. I've generated the prior summary table here to show you that the prior used by PROC QLIM is indeed the prior I requested. Let's try another example. This time I'll manually create the prior information data set and use it to construct an informative prior for the log price coefficient. To do this, I copy the original data set over first so that every other parameter has its default prior. Then after creating the data set, you just need to redefine the prior macro to name the new data set. Then if you run everything as before, you can see that log price is the new prior and every other parameter has its default prior from before. To use this process for models other than linear regression, you have several options. First, see my SAS Global Forum paper for prior selection tips and other models. Then you can modify the autopriorlinear.sas file to tailor it to the model you want to fit. This will allow it to handle transforming all the data for you as well. An easier alternative is to create the prior data set yourself. You have to manually transform any variables first, though. You can use the data set created by autopriorlinear.sas as a starting point to define this data set. Constructing reasonable priors can be difficult, but partially automating the process makes it a little bit easier. All the code for this demo is available on GitHub in the repository at the URL on the slide. Thank you for your time.